So this is going to be a longer presentation because I will cover um, a lot of advanced growth modeling things. I will actually cover concepts covered in Singer and Willett's book, chapters 5 and 6. So let's get started. So chapter 5 is called Extending the Multi-Level Model of Change. So we're going to talk about treating time more flexibly. So far, the data that we've used were traditional multi-wave data where all participants are assessed at equally spaced time points. So we're checking up with everybody at 3 months, 6 months, 12 months, 9 months, 12 months. And that's traditionally what has been done, but that's also traditionally the thing that we could assess with the repeated measures ANOVA, which is problematic on so many levels. So what we're going to look at is number one, variably spaced measurement occasions, where we can either have studies where people are intentionally followed up at different time points because that might be more meaningful for what we're assessing. It could be so event-based, for example. But there could also be just the acknowledgement that in many studies we don't reach people at the same time. Most studies we have some issues with follow-up unless you're doing work in schools and you're assessing everybody who's in the class at a certain day, or you're doing work in prisons. Most of the time we actually have quite some differences in follow-up times and just ignore that in our analyses, and that can be problematic, and using HLM can be very advantageous. Then what we're going to talk about is varying numbers of waves of data. We don't need to have the same number of waves of data from everybody, and this allows us to handle missing data in terms of wave data. And we can include individuals with just one or two waves, while we need some participants, and ideally most participants, with at least 3 waves of data. We will not discard people for whom we only have baseline data, for example. And that is important because that changes how we're doing intent to treat analyses. Then we're going to include time varying predictors. So some things happen over time and not just the outcome changes, but we have time varying predictors and we can easily model those. Explaining them is a little bit harder. There's actually people, and I've got this from reviewers, who say it's too hard, so don't put them even in. But reality is that we have things where meaningful predictors change over time, and it makes sense to model them as such. And then we're going to talk about recentering. The initial status does not always have to be the only thing. We can actually move things around, and there are meaningful applications for that as well. So that's the first half of this lecture. So it's just talking about all the flexibilities, but if we have what we call unbalanced data sets, there can be problems, and that's just due to that exact feature. So the HLM is designed to handle unbalanced data sets. And in most circumstances, and this is absolutely true what Sonia and Willett are putting here on the slide, that is not causing problems. It does the job really well. However, when the imbalance is severe, so you have a lot of people with just 1 or 2 waves of data, you're going to get into problems. There's not just enough information for trajectories in there, and so you might get estimates that are not that great, so you might get large standard errors, large confidence intervals. You might get issues with convergence. It might just tell you it can't find a solution. This also related to how complex your model is, but that can already happen at an unconditional growth model. Um, however, most of these problems don't show up due to the fixed effects. They will show up due to the variance components. So they're using VC as an abbreviation of variance components here. So it's not the fixed effect, it's the random effect. So you want to be cognizant of that. And you will have to test things if the data are what they are, but you really want to make sure when you're collecting data, as always, to get as complete data as possible. And 3 waves of data is really the minimum for doing growth modeling. So you don't want to have too much of a subsample with the 3 waves of data. So there's a really interesting note here, and I want to really say this loud and clear. Software packages might not issue clear warning signs. Singing well, let's say if you're lucky, you get negative variances, and yes, and then you go like, how can that be? Mathematically, that's doable in the algorithms because it always covers a range, so it goes negative. But we know that a variance is a squared number, so it can't be with a real number, it can't be negative. So that means it can't find a decent solution. So that's something you cannot report the model findings on this. People have done this. Don't do it. Another thing is time. Now, I've been sitting with some students asking, like, what is long? It depends on your model. So with those growth curve models, they should converge within a couple of minutes, but some might take longer. That depends on how much you're pushing the data. It depends on how many levels you have in the data. So, but moving up in complexity in models and just let's say you're just adding one random effect to the model and it takes 10 times as much, that's an indication that you're pushing too hard and the data don't have enough information for good estimates. So mostly your model is overspecified given the data, and so the solution is simplify the model. However, you also want to look at your descriptors and the scatter plots and the things that we said because there might be outliers. There might be something wrong in the coding of the data. It's happening regularly to me that we run more advanced models and then find some issues with data quality from cleaning. So please remember that. Okay. So as mentioned earlier and actually outlined on the last slide, it's not hard to put time varying predictors in there. Now, here is the example from the book, and what we have here is we have employment data and depression data. And so what we have in this data set of four variables, you have the ID, you have the month, since unemployment at which the participant was assessed, and you can see that they're all over the place. There are four decimals here. So I would assume that you take the days and then you divide it by 30, and that's how you're getting to the months here. Then we have the CSD, which is our depression measure here. And then we have a time varying variable that is called unemp for unemployment. And you see that for each assessment point, there is an assessment whether the person is unemployed or not. And that's a time varying predictor, just as time, the month is a time varying predictor. So in terms of the modeling, we're already using a time varying predictor, which is time, and then we're just adding another one. And that's really, in terms of the modeling, exactly what's going on here. So now looking at these data more clearly, more closely, we have the first ID here has 3 measurements and all unemployed. There is a participant who has 3 waves, but re-employed after wave 1. Then we have an example here, the last one in here, where we have somebody employed in wave, unemployed, employed, and then unemployed again. And we can model how this employment status changes the change over time in depression. So to assess what's going on, as always, we're going to be fitting a series of models. So we're going to have these time varying predictors and illustrate how that works. And so in this model, we are looking at general change over time in the outcome, and then there will be unemployment as a time varying predictor. So model A is your individual growth model. You can do your unconditional means model to calculate an ICC. It's really not that meaningful, but many people do. Sometimes people call it model 0. So first we're looking at unconditional growth model, no substantive predictors, and then we're adding unemployment as a direct effect and assessing that. Now, in this case, they chose to put unemployment in this model as a direct effect that's fixed. So no random unemployment factor here, and that's up to you. We talked about we could just run a model that only has unemployment in it and see if the random effect is significant, how well the model converges and things like that, and then put these two predictors in together. So now we have two time varying predictors, two level 1 predictors in here. And then the third step in this case is to put in an interaction effect on that first level. And so now we're looking at there's a general change over time. There is something that is due to the employment status at that point, and then there's an interaction effect. Is like how do the two things interact? Now the last model allows the effect of unemployment to vary over time, but it does it by allowing a random effect as well. So not everybody's reaction to unemployment will have the same effect over time. So what does this look like? We're going to look at the model B, where we have two time varying predictors as direct effects in there, and time has a random effect, unemployment is a fixed effect. So we're going to be talking about the population average rate of change over time, and then we're going to look at population average difference over time in the outcome, which is depression. So how can we understand this graphically? So what's really nice here is we can now draw different possibilities. Time changes linearly over time, so everybody will get that. But we have different patterns that were actually outlined 2 slides ago with the different possibilities that people have. So looking at those 4 graphs down there, everybody in this study was enrolled at a time when they were unemployed. So we have the following patterns. The first one, consistently unemployed across the 3 time points. And so what you get is unemployment is always 1. So if you would create and calculate the prediction equation, you would always add the gamma to 0 so to the slope, because that's an additional change over time. Every time it will be constant. Now, the unemployment beta goes away if somebody says they're reemployed at 5 months, and so then the trajectory jumps down. It has the same slope, but there is this decrease, which is gamma to 0. So you're not adding gamma to 0 because unemployment is 0. Now, the same thing happens just with a later shift in time of somebody who's reemployed at 10 months. And then the last finally shows somebody who is unemployed, reemployed, and then unemployed again. And so what you see is that we have a consistent change over time, but different elevation. And so what you already see is a discontinuity due to a binary time varying predictor. So here's now the output when you run this model. And again, will it run everything in SAS? So this is SAS output put into a nice table. And they're actually adding model A and model B. Remember, model A is the unconditional growth model, and model B adds unemployment as a time varying predictor here. So looking at this, there is a monthly rate of decline. And what they're also pointing out is that once you're controlling for this unemployment, this decline in depression is cut in half. So it's lower, and unemployment status over time plays a large role when you look at this effect. It's 5 points if you get reemployed. And so what we see here is that we have 2 significant predictors in here, but there's quite a change because we're explaining some of that rate of change with the unemployment here. And the other thing we see here is a goodness of fit. We see that the deviance is going down, the AIC is going down, the BIC is going down. So model A is a much poorer fit. They actually ran maximum likelihood estimation and then calculated a delta in deviance and used a chi-square test to see whether this is significant. So now we have the two prediction equations spelled out. We have for somebody who's consistently unemployed, we have a person where we have two components added, so that person's CSD would be higher, sorry, on average, and then there is a decline of zero point 0.2 over time. Now, somebody who's consistently employed would have a prediction equation of having that lower starting point and then the same decline over time. So on the right graph, what you see is that the person who's consistently unemployed, that would be a green graph, which is underneath the red piece as well. And then somebody who's consistently employed would be at that blue graph. There's a dotted line in the beginning because, as I mentioned, everybody who was enrolled was originally unemployed. So there is really nobody who could be at that front end. But then what you see here is that actually when people get a job, you will see that they drop from one of these lines to the other. So these two groups, people who are consistently unemployed and those who are employed, those are prediction equations, and you're jumping between depending on your unemployment status. I want to talk briefly about the variance components, and I just started editing this slide when I was preparing it for recording because I'm starting to disagree with Singh and Willett on several of these things. So you want to look at the variance components, and then what we've done traditionally we've done a change in those variance components to get a sense of predictability. And so they haven't done this here, so they talk about it though. So when we're going from model A to model B, your within person variance goes down. So there's more variance explained here. What happens in this case, your level 2 variance goes up. And we talked about these things going in different directions. So we're now modeling the patterns of unemployment, and it is highly likely that those patterns of unemployment are related to person level characteristics. There are probably characteristics that influence who is getting a job in this time period and who is not. That could be level of education, that could be age, there could be so many things in there that actually are related to this phenomenon of change in unemployment. So we're modeling pieces of that by modeling that time varying predictor. So while these are interesting, they are oftentimes very hard to interpret, but it's good to look at them and see what's happening. And starting to think of why, because you would want to know theoretically, how can you explain changes such as these? So let's look at Model C. Now we're asking the question, might the effect of a time varying predictor vary over time? So that's what we're asking if we're putting in a level 1 interaction effect between unemployment and time. So we're allowing the effect of unemployment to vary over time. And so what we get is a traditional one level interaction effect. And those depend on what you're interested in. So as you can see in the red box on the left, there are two possible completely equivalent interpretation. The first one is the effect of unemployment differs across of occasions. The other one is the rate of change in depression differs by unemployment status. So you want to think through what question are you asking to know how you're interpreting this, but there are different ways of looking at this. You need to be very careful about the error structure. We're adding another level 1 parameter to capture that interaction, and so we need to be careful about this. And so Model C doesn't account for that. Why is that so important? Because we said that time is a random effect, and now you're putting in an interaction term with time. But we'll get to Model D about that. Here is the output from Model C, and what you see at this point. Now, the main effect of time is positive and not statistically significant. I love the list of question marks and exclamation marks. We have a interaction effect between unemployment and time. And then we also see that Model C has, they call it much poorer fit, I would say. Um, and that's significant, but it's at 0.05. That's the level. So we're looking at two um, prediction equations, again, to outline what's happening to those who are consistently unemployed and those who are consistently employed. And we see that we have a decline in depression over time in those who are consistently unemployed, and an increase in depression on those who are consistently employed. So maybe the grind of work is hitting again. It could also in the subsample that there is the fear of losing your job again, which could also contribute to this. And then we have the red trajectory, which shows somebody who gets a job at month 6. And that would be the trajectory that is predicted by our model for that person. So I want to talk about what Singh and Will are doing with the next model. So given model C showed a non-significant change over time effect, they asked the question, should we remove this? Which is really the slope when unemployment is 0. So they say yes, but then they say, oops, we have a problem because now the area structure doesn't match our model. And so they say to actually adjust the error structure to fit that. In general, I wanted to just note that HLM7 doesn't allow us to do within level interaction terms. So at this point, you will have to move into a different software anyhow. But SAS and other programs can easily deal with this because you've already seen this from creating your job aids. They don't really know or care about what level predictors are on, so everything is a free-for-all, but you need to know what you're modeling there to make the right decisions. But this is their solution, and so then in their Model D, they have only a direct effect of unemployment and an interaction effect between unemployment and time. Now, I personally would leave the time component in and see if the model can handle it, and only take it out if we're running into power issues. But in general, they're also talking about the problem is now that we're getting model fit issues. So let's take a look at the output. So here is the output from Model D, which remember now they took out the time effect that's direct. And now they have two significant predictors again. And what you see that there is better model fit of Model D over Model C. What we have now on the right side, you see now that we have no change over time in those who were employed, but we have a decline in depression in those who were unemployed consistently. And then you have, again, people jumping across these levels if a change in unemployment status happens. So this is how you can model these sequences, and then how you can create graphs and prediction equations to help you understand what's going on. So I want to talk about centering, or as it's outlined here as recentering, the effects of time. So far, everything we've looked at have centered time on the first wave of data collection, which we many times call baseline, and that allows us to intercept as the individual's initial status. And this is the most common and in many, many cases the most meaningful approach. It's not the only way of doing things. So sometimes you want to center time on a value that ensures that your growth parameters are meaningful, but there are other options. So some people have used a middle point to focus on an average value of the outcome during the study. I don't see the meaning of that, but that's fine. Sometimes there's an endpoint status, and that can be inherently meaningful. I've seen studies that look at programs' effect over time on college readiness. So you're really interested in where are people on average at the end of the program. So that is something that is a meaningful thing to interpret. If, for example, in school programs, usually where there is a goal of decreasing inequalities, and so that would be a meaningful shift. So here's Sing and Willard's example about a reading program. And what they have right here now is, so we have wave data. And that's usually in our data the very first kind of time indicator that we have, and that's really good for data processing, but not intuitively meaningful given here we have three measurements in time for every day. So 8 a.m., 3 p.m., and 10 p.m. So what then happens is that this wave data gets split up or pulled together from other data in terms of having a day variable and having a reading variable. Now that gets recoded into a time of day, and in this case it got recoded as 0 for 8 a.m., a 0.33 threw it into that kind of day, and a 0.67. Not sure about that, but whatever works for people. So then there is this new time variable, which is the one that we will be modeling because you can't put these two things in isolation, the day and the time of day. And so everybody gets this coded, and it pretty much is just adding the day and the time of day together. So it really makes sense to have these fractions in there or decimals, and then you can just add those two columns of day and time of day to get the time that we will be modeling. And so that can be interpreted as times days passed since the beginning of the study. And so now in this case, where they're showing here two ways of centering. One is in the midpoint of the study. Again, for whatever reason, maybe somebody wants to see at the midpoint of the study where people are in terms of their average status. And then at the end of the study, so what you're doing is you're putting your 0 point and just shifting around to where you want it to be. So how does this change interpretation? And so we have this model. There's a treatment variable. Again, this is this reading program. And so what is the impact of that? It will have an impact on not on the slope, but it will have an impact on the intercept. So the raw metric is the individual, in this case, mood is the outcome at time 0. So it's at the initial status. If we're doing midpoint centering, then it's the individual's mood at that time. And then when we're at the end point, then it is the individual's mood at the final point. So as I was outlining already, it depends on what you're interested in. And so you might actually run different models to get that. You could also just do some algebra and get to the same, actually just arithmetic and get to the same answers. So let's look at the output. And what you will see is that you will get different intercepts, different impact of the treatment, the direct effect of the treatment, which is at baseline. And then what we see too, in terms of the change over time, there is no difference. So choice of centering has no difference on the following things: goodness of fit, estimates for rate of change, within person residual variances, and between person residual variances for the slope. So any change happens on the intercept. So if you don't care about interpreting your intercept majorly, it actually doesn't matter. Also, traditionally, we will talk about baseline or initial status. So what you see then, if you're drawing this, you get one graph because the change of time is exactly the same. The question is just where there is the 0 point. So your intercept now, as you can see, is this difference that happens at different time points in there. So you have an intercept difference of negative 0.3 at 0 days. This is our natural metric. So this vertical line here, then it gets turned around. It's positive in about at 15, so it's a little bit larger, and it gets even larger here as these two trajectories diverge over time. So that is what we're getting. Now, what you have to be careful with now is significance level, because significance depends on the effect size. And if you move this around, what you can get is that at certain points, there was actually not a significant difference between the treatment and the control group. And then at other points, it is significant. So again, it depends on your research question. So this is then the end of part one, and this is what an overview of chapter 5 in Singer and Willett, and we looked at the flexibility in time, the flexibility number of time points, modeling time varying predictors, and centering of time varying of time.